So hello and welcome to this Prism Sound Wednesday webinar. My name is Simon Woolard. I'm an applications engineer at Prism Sound in the UK and I will be today's moderator. I will shortly introduce you to my colleague Doug Audon, who will be presenting today's session on the title of Preventing Pops and Glitches in Broadcast Audio, in Digital Broadcast Audio. So I will introduce you to Doug in just a second, but before I do that, I just wanted to ask you for a little feedback. We have a little question for you here before we get started. So I'm just going to switch screens so that we can actually look at Doug's computer. So I'll just do that now. And Doug, do you join us on the line?
Yes, I'm here.
Okay, we'll introduce you formally in just a second, but could you please show us the D-scope screenshot where we're going to ask people if they can spot anything wrong with the signal that we're showing to them.
There you go, Simon. Yeah, what we have here is a scope, a time domain display, as well as a signal generator.
Okay, Doug, so could you please turn on the signal generator? We're going to have a look at the time domain trace of that signal, and we should also be able to hear that signal, albeit we are listening down a telephone line, so it may not be 100% crystal clear, but could you just turn that on and we'll have a listen to it for a couple of seconds, please?
Yes, here we go.
Okay, thanks, Doug. So I'm going to just start a quick survey, and on the basis of what you have just seen and heard, I'm going to ask you whether you perceived any problems with that signal there. Did you think that signal sounded okay? Did it look okay? Could you just please fill in that survey for us? And the survey is anonymous. We just want to just engage you a little here and just see what you thought to that signal that we just heard and saw there. So that survey will run for a few seconds just to give you a chance to reply. As I say, we won't be embarrassing any individuals, so please do fill that question in. It is totally anonymous. And I'll just leave that running for a few more seconds, and I'll stop the survey in 3, 2, 1. So the survey has now ended, and let's take a quick look at the results. So it would appear that of those of you that responded, the majority think that that signal looks okay, free from pops and glitches. Now, of course, this is a somewhat loaded question, and we've chosen a signal there that does actually look okay and sound okay, and hopefully by the end of today's session we'll have proven the fact that just visually inspecting and listening to a signal may not be sufficient to determine whether or not there are any underlying problems. So I'll close that survey for now. I shall just switch back to my screen for a second. And I just want to introduce you to Doug Audon now, who will be taking you through the rest of today's presentation. Doug is the head of Prism Sound's US Sales and Support Network, and he joins us on the line from Fort Worth, Texas, where he is based. And I would ask you to now welcome Doug. And Doug, could you please take over and take us through the rest of today's session? Thank you.
Yes, Simon, thank you very much. I'm going to transfer my screen now here. If you can just, can everybody see my screen now?
We see your screen okay, Doug.
Okay, great. Well, to begin with, as Simon said, my name is Doug Audon, and I want to thank you all for attending today. We appreciate your time, and what I'd like to do is dive right into our presentation here and give you a quick idea of what the agenda is. First, I'd like to begin with an introduction of just what causes pops and glitches and dropouts. We'll spend a little time on the history of AES digital audio. Then we'll actually drill right down into the format itself, look at the nuts and bolts of the format, talk a bit about channel status, metadata, and this can be a real nightmare because the the pops and glitches that you experience can have nothing to do with your design or your transmission paths, but channel status itself. And then we'll also try to give you a better understanding of the eye pattern, or maybe introduce you to it if you're not familiar with it all. A technique used in the communication industry quite widely. And then we're going to do some actual real-world detecting of pops and glitches using using the D-scope and our other devices. So, introduction. What causes pops and glitches? Well, to begin with, jitter in source clocks. Now, jitter in source clocks can come from a number of things, but a likely culprit, obviously, is a defective piece of equipment, poor design. These are the things that contribute to source clock jitters. And then jitter and carrier degradation in digital interfaces. This has to do with the transmission lines, the cabling, patch bays, anything that's in the signal path. And of course, we touched on those channel status problems, and we're gonna spend some time on that later. And asynchronous digital clocks, where you have clocks that are running asynchronous, they're not locked, and are drifting in and around each other, which can cause random pops and glitches. So we need specialized digital audio test equipment to investigate these problems. As Simon mentioned, your tools that you've been using in the past for analog troubleshooting are just not capable of tracking down these problems. Let's take a look at our actual setup here that I have on my bench. I've got a D-scope Series 3 digital and analog test system, which is married to a PC running the D-scope analysis software via USB. And then today, the device under test is just a 300-foot spool of AES cable at the correct impedance, 110 ohms, and so we come. And I might mention the D-scope pictured here, as well as the one I have on my bench, is both analog and digital. The analog portion is appears up here at the top, but today we're going to be using the AES XLR, AES3 XLR output, and we'll be coming down the cable around and around for 300 feet, and then out and into the DSA-1. Now, this is a battery-operated handheld instrument that mimics the measurements that you'll be seeing done on the D-scope today, and we're going to use that in the loopback mode, where it can be inserted in the signal chain without disrupting anything, and you can actually monitor your quality of your transmission and carrier path while you're actually on air. And then out of the DSA-1 and back into the D-scope for analysis. Now, with respect to the history of the AES digital audio, before I dive into that, what I'd like to do is take some time to talk about what we just saw and heard at the beginning of our presentation. Conventional analog test equipment, as I mentioned, and measurement techniques, including listening with your own ears, cannot be used to assure you that you are broadcasting a robust and pop glitch-free program. You may think everything is fine. You step away and you're off the air. Well, how is this possible? Well, unlike analog audio, digital audio does not degrade gracefully and gives little or no signs of failure. And what's more, this can happen so infrequently, you might have to wait for days to experience or catch a failure. Now, let's go back to the opening real-time measurement here for a moment. I'm going to pull that D-scope up again, turn the generator on. I'm going to turn that tone down so I can talk to you. Trying to talk over that, it's rather difficult. But as we can see, this sine wave looks like it's in good order. However, what I'm going to pull up now is our distortion analyzer. And you can see we have some red alarms that are flashing when it's making the distortion measurements. And what we've set up is some very tight limits on the distortion measurements such that we can catch anything that's gone wrong inside that signal that we may not be able to hear or see. But that in itself, I mean, that's one tool. Tells us there's something wrong, but that in itself is not complete. We need other tools, and that's where the D-scope offers a number of other ways to take a look at the transmission path to determine whether there are problems. So I'm going to bring up something that we talked about earlier, which was, or at least talked about the eye pattern. This is a measurement that's made using a high persistent wide bandwidth storage scope, and the D-scope emulates that. We'll get into depth in this later, but you can see these red boxes that appear, and those red boxes are the AES limits for receiver acceptance. And you can see that our eye pattern is walking on those boxes. So that tells us that we've got some problems. So here's another indication that the D-scope provides and affords you in troubleshooting your system. And again, we're going to get into all these things in detail later. The other thing that we talked about is the fact that you might have to wait for days, literally, to have these problems occur. I mean, sometimes they hit you left and right, but there are times when it may not pop up, or it pops up at a certain point in time. So another tool that the D-scope provides you is what we call our event logger. And this can create a log file, and you can see that we are logging errors that we have asked it to report to us. Now, in this case, we're asking us to report the errors in the distortion breach as well as infringements on the eye pattern, and these things are date and time stamped. This is very important. So we are able to determine just when this popper glitch happened or error happened, and then we can tie it right back to the time of day and the date. Now, this can help considerably, because typically this is possibly done or manifested itself because there's some kind of electrical disturbance possibly, or something's being switched in the router at a particular point in time. But in the case of electrical interferences, you can this eye pattern that we're looking at, we're looking at the data stream. These should be all square edges. Obviously, that's not the case. We're seeing these very long rise and fall times. And these rise and fall times mean that the comparator and the signal, the pulse, is spending a lot of time around the zero cross. So any disturbance that happens during that time could possibly trigger this pop or glitch or even mute. So having taken a look at some of those tools, let's get back into the PowerPoint, and let's talk a little bit about the history of the AES digital audio. I think it's safe to say that the AES3 format is the most prolific standard for interconnecting digital audio between professional equipment. And the the quality, the audio quality of a system designed around this AES3 format is determined by the converters employed and the system design considerations given to the digital transmission of the audio. Now, this webinar is just going to focus on the test methods surrounding the transmissions aspects of this subject. We're not going to dive into analyzing A to Ds and D to As. That's another whole subject in itself. So this concerns itself with the transmission aspects, and I hope that this will be a straightforward and easy to understand webinar and leave you with a practical working knowledge of the AES digital interface, and hopefully spark your interest to learn more about this relevant subject. Now, having said that, if we can roll the clock back about 40 years, in the early 70s, digital recorders were just coming into the marketplace, and as other manufacturers brought in these recorders, there was lots of discourse relating to the methods of digital audio channel coding centered on, of course, these recorders, which they needed packing density efficiencies, and there were intricacies that related to rotating and stationary head recorders that were in the marketplace. And then digital consoles appeared in this space, and at that point there was no way to get audio back and forth between these devices in the digital domain. Everything had to be done in the analog domain. Excuse me. So the discussions in the late 70s and early 80s turned to methods intended for allowing the transfer of this audio, and unlike the previous discussions, channel coding for the transfer of digital audio between recording and mixing devices demanded other technical configurations. So I think what we should do now is just dive into the format and see just how they met this challenge. The AES3 2003 ASB format. This has been obviously revised a number of times over the years, but in essence it stands the way it was first implemented back many years ago. So the format itself, keep in mind that this the format, and I think what I'll do is I'll use 48 kilohertz here. I know if you're in the broadcast industry, you're either working with 44.1 or 48. It's rare you're going to move out of those sample rates. So just to give you some idea of the bandwidth, we're looking at a data stream that contains a frame format that contains A and B audio sample, and this audio sample can be anywhere from 16 to 24 bits. And in this frame, there's also coordination signals and metadata, and that equals one AES frame. So there's the frame, A and B channels, but we want to drill down and take a look at what's in one of those subframes. For all practical purposes, these frames are identical. So we'll take a look at the A channel data, and now it's comprised of 32-bit periods, of which 4 are a preamble, and this preamble it contains what we call an X preamble, a Y preamble, and a Z, and this allows us to identify the A and B channel and something called a new block, which we'll get into later. Next, we've got the audio sample itself, which can be between 16 and 24 bits, with least significant bit first, and the coding that's used. Remember, we talked about digital tape recorders and ways that people got digital audio around prior to the proliferation of this equipment. And typically the way that was done, whether it was done on a circuit board or outside, to the outside world. Logic zeros and logic ones, or zeros and ones, were represented by high and low states. And then the clock was sent on another path that would tell us where those zeros and ones actually appeared in the data stream. Now, problems with this this type of coding is the fact that you've got the clock and the data stream taking two paths. They can be two different lengths. They can have different delays. There can be problems on one. At the end of the day, you have the possibility that they are not in sync with one another. So when the AES Standards Committee looked at this, they decided that the best way to handle this would be to embed the clock inside the coding of the data. And the way this is done is with a biphase mark encoding scheme. And this is interesting in itself and goes way, way, way back to before World War II. But in essence, what it does, it allows us to represent zeros and ones, not with high and low states, but with transitions. So we have a bit cell, and in this case, it is a 0 because there is no transition. Now we have another bit cell here, but we can see there's a transition in the middle, and that represents a 1. So that is the way the biphase mark encoding system is implemented, and as a result, the clock rides within this bit stream. So that's an important part of the way the AES3 standard is implemented. Moving on now, the last 4 utility bits that are in the frame, in the subframe, are the validity bit, the user bit, and the channel status bit, and the parity bit. So what I'll do is I'll focus here on the channel status bit, because this is where the bulk of the metadata is presented. Now there is a validity bit that is transmitted, and I'll relate a story that relates to that as we get on in the presentation. But the validity bit, in the early implementation of the standard, there wasn't a clear idea of whether data would be sent in the audio portion of the stream. So a validity bit was incorporated such that if that flag invalid is made, you know not to decode the audio and present something to the ears that would be unpleasant, to say the least. The other bit, the user bit, this is undefined. You can stick anything you want in there. And then, of course, the parity bit has to do with an even parity that's presented in time slot 31s, such that all preambles will start at a transition in the same direction, and that's important for identification purposes. But again, channel status bit. This channel status bit, there's only one bit in each subframe, but after 192 frames, we have something called one block, and that block brings us to the channel status metadata. So if I can, we'll dive into this. And like I said, this is kind of a favorite part of my presentation, because the channel status is really a hidden minefield. You could have all your P's and Q's and T's and I's dotted, and you'll still possibly be tripped up by something in the metadata. In other words, the handshake between one piece of equipment and the other. Just to get back to this slide where we were talking about it, where it exists in the data stream. After 192 frames, we get one block, and that block represents 24 bytes of channel status. Now, the way the descope, and this is another powerful tool that's incorporated in the D-Scope. What you're looking at here is a dialog box that represents those 24 bytes. And as you can see, this is all in plain English, easily to understand. And I think the best thing to do now is just get back to the D-Scope and show you some live measurements and how we go about tracking down problems in channel status. So here we are. We're back into our, you can see our event log is still running. And I think that's maybe this is a time to point something out here before I switch to the channel status display. This event recorder is not like a chart recorder that runs out of paper. There's a lot of solutions today where they do event logging, but they perhaps stop at 24 hours. And this is quite frankly is not sufficient. You need to be able to possibly stick one of these event loggers on a system for even up to a week to find out what's going on and when. So having said that, let me come up here to channel status. By the way, these buttons that you see at the top, I created these. This is another tool that the D-Scope analyzer affords you. If you, for instance, if in your plant and you're the chief engineer or someone who's been assigned to the task of tracking down these types of issues, you can create these buttons to perform specific tests. And by the way, the DSA-1 has the same kind of functionality to perform specific tests that you're confident of the technique, the procedure, and the consistency, so that a layperson or someone who possibly is not familiar with what needs to get done can simply press a button and get to the test that you need to record. So now we're actually looking at a live representation of this dialog box I was talking about before, and this is on the input side. So we're looking at the channel status and we're reading it, what's coming down the cable or from the last piece of equipment. And you can see we've got some red red highlights here, and these highlights are accomplished by this drop down. Again, another tool here that we afford you. You can highlight differences from the output, from the other channel, reserve fields in use, or inconsistencies. In this case, I'm using inconsistencies. And probably the best way to explain what's going on here is to bring up what I'm sending down the other side. So if I bring up the output channel status, if you can think of this is a dialog box that writes to the channel status. This is a dialog box that looks at the channel status and reads it. So I'm in a simple mode here. This is very common things that people normally want to address, but I'm going to bring up the advanced portion so you can directly correlate to what we're seeing in the input channel status in its advanced mode. So the first thing I want to look at is byte 0. Byte 0, we got a flag here. It says 44.1. What that's saying is that the metadata is telling us that the sample rate should be at 44.1 kilohertz. But if we take a look at the actual live measurement here, we can see that we're actually at 48 kilohertz. So the D-Scope instrument is intelligent, and it is able to discern that the metadata is telling us that it should be at 44.1, and the actual bit rate within the frame rate, the sample rate within the data stream is at 48. So this is very powerful. It allows you to quickly identify this type of problem, and when you have different inconsistencies in the sample rate on a piece of equipment, depending on how the manufacturer is implemented, this may just mute. It may not pass audio. So if we're trying to analyze what's coming down from the last piece of equipment, this is the dialog box that we're looking at. But now if we're trying to find out how a piece of equipment behaves when we give it inconsistencies or various metadata, we can make that change over here. So if I if I write 48K into the metadata, you can see the inconsistency goes away. The D-scope knows that 48 and 48 are consistent, and you don't have to bother yourself with it. Now, I'll just point out one more thing with respect to this. In byte 2, we've told the next piece in the chain that the word length is 16 bits. However, that's gone red here too. And what I've done here in our digital input display, we have a display that shows bit activity, and I've masked it. I can do that here. I've masked it to 16 bits here, so you can readily see that we have 20 active bits in this. And again, the D-scope, intelligent, knows that there's 20 active bits in the bit stream, yet the metadata is wrong. So now there's a couple of other things that we were talking about with respect to, and I just want to bring up the other portion of the display here. We've got something here on the digital output side that allows us also to address, if you remember, the validity bit. So I have again, I'm writing to the not to the channel status now, but I'm writing to the bits in the stream. There are those last 4 bits, and I'm telling the next piece of equipment down the line that channel A is invalid. And we have that indication again here. Up here you can see the validity bit is gone red on channel A. So that immediately if you saw this, if you interface the equipment to your device and you saw this validity bit, you know immediately you've got some problem. Now that doesn't necessarily mean that the problem will manifest itself, and I'll get into that in a minute. The other thing is that you want to be able to verify is user bits. So if I click on user bits here, you can see my user bits go green, telling me that I've got a transparent user bit data stream as well. So I'll just shut those off for a minute. Now, let me get back to this validity bit for a minute. I was giving a presentation at a broadcast manufacturer to some people who were just getting ready to dive into HD radio, and I was talking about this validity bit. Somebody raised their hand and they said, "Hey, that happened to us." And ironically enough, they actually owned a DSA-1, our portable handheld device, and they said they were evaluating 3 pieces of equipment and they were sticking it in the chain one at a time. And when they put this one in, every time it wouldn't pass audio; it muted. So everybody's pointing their fingers at this piece of equipment that muted, and as it turned out, they pulled out the DSA-1, put it into the signal path, and discovered that there were validity invalid bits set on the piece prior to the chain, prior to the evaluation piece. So what was happening was the only manufacturer that was complying to the spec was actually muting it. So the problem actually existed with the handshake that was coming from the equipment in the other part of the chain. But without some kind of tool like this or what's provided in the DSA-1, it's impossible to determine what's going on. So having said that, let's get back into our PowerPoint. By the way, if you have any questions, I know I'm racing through this stuff, but if you've got any questions, don't hesitate to communicate with us using the NetViewer chat window, or just jot them down and we can discuss these with you at another time. So understanding the eye pattern, I believe Simon's got a question for you here. Simon, is that the case?
It's absolutely is, yes. I just have another quick question for you all. I'd be grateful if you could send us your answers. We just want to try and judge from your perspective, your level of experience with dealing with things like the eye pattern. So I've just asked you a quick multiple choice question, just asking you to tell us what you think the eye pattern shows us. So once again, this survey is anonymous. We shan't be embarrassing you as individuals if you don't know the answer. We're just trying to gauge the level of experience of the audience here today. So I'd be grateful if you could answer that question for us as quickly as you possibly can. We'll let that survey run for a few more seconds. We've got the responses coming in, so I'm going to let that run for just a few more seconds. And 3, 2, 1, I'll be stopping the survey now. So let's just take a quick look at those results. Doug, do you see them?
There we go.
So you can see that there are a range of responses to that question, and some of you do have the correct answer. The correct answer is that it is the digital audio carrier waveform. So we're actually looking at a superposition of many passes of the electrical waveform that is transmitting the AES digital audio signal. So that's probably enough from me. I will allow Doug to explain that further, and hopefully by the end of the session we will all understand entirely what the eye pattern display is showing us. So I shall hand back over to you now, Doug.
There we go. So the eye pattern display itself. By the way, I think that was a trick question, Simon, because I think I got it wrong myself. But hopefully I can explain what the eye pattern is all about. As I mentioned, actually eye patterns are used quite frequently in the communications industry to analyze systems such as the data stream in the AES standard. And if you bear with me for a minute, what you may not know, depending on whether you've ever looked at an eye pattern or not, but an eye pattern is actually used in conjunction with a long persistent storage oscilloscope that has sufficient bandwidth to handle the data stream. So this is usually a very wideband scope and a storage scope, and as a result it's a very expensive piece of equipment and doesn't wind up on most benches, although if you've got one you can count yourself fortunate, but it's not typically found on the bench. And this is another great tool that the D-Scope affords you, is the ability to look right into the data stream as if you had such a tool. I might also point out that even if you have a tool like a high bandwidth storage scope, there are triggering issues that you have to take into consideration, and as a result, if you don't trigger on the signal properly, you can actually get totally wrong results, or if nothing else, inaccurate results of the jitter that you're measuring. So the D-Scope takes all that into consideration, and you don't have to concern yourself with any of that, and you're just presented with the data stream. So that's what we're looking at here. We're looking at the carrier display, but the data stream that we're looking at here is a static number. In other words, in the real world, these bits would be moving from 0 to 1, 1 to 0. So we have a bit cell, and as I mentioned, this bit cell running at 48K has a bandwidth of about 3 megahertz. And then the biphase mark cell rate, in other words, where we have a transition where this would equal a 1, that data rate is actually upwards of 6 megahertz. So you get an idea of the type of scope that you need to present this kind of information. And then, of course, we also want to look at the carrier amplitude, because this is important to know what the degrading that's going on due to DC resistance of the cable, the insertion loss. So if you can imagine now for me, as Simon mentioned, that the eye pattern is actually because of the persistence of the scope, it looks at this number that's passing by, and then it looks at the next number, and it lays them one right over another. So in the next in the next frame, this could be a 1, and this could be all zeros, or they could be all ones. So what I've tried to represent here is an ideal eye pattern, and showing you here that it actually, this particular end result that you're looking at comes from the storage scope, where you're laying one frame after another right on top of one another. So what we're looking at here is, again, a bit cell, a biphase mark UI, and ideal carrier amplitude. But keep in mind, unlike the last slide that we had, the bit cell here now sometimes is a 0 and sometimes is a 1. So depending on what the data contains, you get this pattern that you're looking at, which is ideal. Now, what I've done here is I've placed the ideal pattern next to a real world. We threw some cable at it. All right, so now we have some cable. Of course, the bit cell and the cell rate, none of that changes, but the ideal carrier amplitude obviously is degraded by the cable. So we can see that has been reduced, and then the impedance of the cable, primarily the capacitive reactance, has degraded the rise and fall times of the bit stream. So here we're looking at rise time, fall times. They're no longer square edges. We've also reduced the amplitude of it, and this all tells us a story about what is going on in the data stream itself. So now we know what this thing looks like. Let's take a look at just what all this means. Jitter. That's the thing we're trying to establish here as the culprit for causing these pops and glitches. And there's two sources. One is related to clocks, and I choose to call that source-related jitter here. And then the other is cable-related jitter. And we're going to show you just how those two things relate to one another. So let's start with the clock jitter, FS jitter. Ideal sample clock running exactly and precisely at the same time it clocks off. But in the real world, an actual sample clock will be varying around that specified clock frequency. And that particular bit of change that occurs in real time is phase modulation, known as jitter. So the jitter can be plotted versus time down in this lower portion of the diagram. So that's what happens in the real world with clock jitter. And of course, as I mentioned before, this could either be because it's been poorly designed, or it's possibly defective in some way. Now, this diagram illustrates a form of jitter that is a direct consequence of the interaction between the high frequency losses of the cabling and the clock data embedding of the coding scheme. Now, we've got two alternative segments of transmitted biphase mark encoded data here up on the screen. One's carrying a binary sequence of 000 and the other 010. Now, if we take a look at the resultant cable voltage after it's gone down, say, a poor quality cable or just a very long cable, the high frequency losses of the cable result in the familiar charging-discharging pattern at the receiver input. And when we get down to the comparator and we try to recover this data after slicing, it can be seen that the timing of the latter two transitions in the one symbol has been displaced with respect to the correct position when the system is 0. And of course, this results in phase modulation. So in essence, cabling itself can represent itself as jitter just as a jittery clock. And this effect happens as a result of the different pulse lengths being present in the biphase coding stream. So if these were all zeros or all ones, this error wouldn't occur. However, again, this data is constantly changing, and as a result, we manifest itself as phase modulation in the jitter spectrum. Now, back up here for a minute. I just wanted to say that this particular type of jitter is got a number of names. It's known as data jitter. That's what we happen to refer to it in our instrumentation. But it's also called cable-induced jitter, inter-symbol interference, and pulse smearing. Now, measuring this jitter, this is very important because obviously, if you have jitter, you want to know whether or not it's coming from a clock or from a cable. But this is not very straightforward when you're looking at the eye pattern. In fact, when you look at a typical eye pattern, and if you're in the audio portion, the jitter that is represented by the width at zero crossing is actually the combination of clock jitter, FS jitter, and data jitter. So what I'd like to do is explain how we go about, and actually you could as well, to determine whether you got clock or data jitter or both. So if we look inside the preamble, if you remember the preamble, and the parity bit allowed for the same transition in the preamble, and as a result, if we look inside the preamble where there is no audio data, and we measure the width at the zero cross, that will give us the clock jitter. However, if we take a look at the portion of the bit stream that has audio data, we can measure the width of the zero cross, the trace of the zero cross, and we will be measuring data jitter. Now, keep in mind, data jitter meaning there is audio data inside this bit of the bit stream. Obviously, that's where the name comes from. But keep in mind that data jitter also includes clock jitter. However, since we know what the clock jitter is, we can subtract that from the data jitter and know what is being induced by the cable. Now you can go into your storage scope, or you can put cursors on our D-scope display, displaying this this eye pattern, and make those measurements. But again, another powerful tool that we've got in the D-scope allows us to actually make that measurement and present it to you in scalar numbers. So this particular reading here is measuring the data jitter, which is, I'm going to round things here, 25 nanoseconds. And then the FS jitter over here is at 7 nanoseconds. Now keep in mind that the data jitter includes the FS jitter, so that means we've got about twice as much jitter in the data analysis than we do in the clock. So obviously the degradation that we're seeing here is primarily induced by the cable and not the clock. This is invaluable when you're trying to track something down. And by the way, all of this can be done either with the DSA-1 or the D-scope while you're running program, because this can be in a loop-through mode inserted into the signal chain, and we can be looking at this and measuring these quantities while you're broadcasting. All right. Now let's get into some real-world measurements here, where we're actually going to detect we're going to show you how you can go about detecting pops and glitches. The first one we're going to tackle is non-transparent paths. and let me say something. Transparent paths are quite straightforward. They consist of routers, cabling, any piece of equipment that does not alter the bit stream at all. So we'll tackle the non-transparent path first, because that is the most difficult, where, say, you've got a sample rate converter on the input, or you're in a console, you've got a level control, or you've got EQ, anything that manipulates the path. So we just can't simply put in a number and look for the number on the other side. So again, we've got the D-scope married to a PC with running our software via USB, and we've got a non-transparent system. And so what kind of stimulus are we going to use for this? Well, like in our earlier presentation at the start of the webinar, we're going to use a sine wave. And what I'm going to do now is switch over to a live measurement, back to the D-scope. I'm up here on non-transparent path. Hit that shortcut button, and we'll load this. And what we're looking at here, I'm going to turn the D-scope up again just so you can hear what's going on. So there's the 1 kilohertz. Looks good, sounds good, and we've got an eye pattern here that's being painted right now. You can see this eye pattern is obviously portraying the fact that we're not stepping on any of the AES limits for jitter and level. So we're looking good there. That's a great tool. We've got nothing going on in our event log. Our distortion seems to be stable. Everything seems to be fine. Now, so what I'm going to do now, and this is something we really didn't touch on. I kind of breezed over this in using this, but what we're going to do now is we're going to take the digital output carrier and we're going to degrade it. This is possible to get. This is another tool in the D-scope. If you're trying to find out where a piece of equipment falls over, you can add jitter in all types of forms, noise, sine waves. You can add differential interference, common mode. Again, we won't get into this here today. It's too lengthy a subject. But what I am going to do is I'm simply going to add 1 nanosecond more of jitter into this signal path. And having done that, that's enough. 1 nanosecond more of low audio band jitter has caused my eye pattern to close down onto the limits. I'm now seeing alarms being fired off by my distortion analyzer. I'm seeing logs that are coming into my event log recorder. My sine wave still looks good. I've got an indication up here in my digital inputs panel where I've got biphase violations. I won't get into that because we could spend an evening on that. We've got, but we do have an indication of it, and I can tell you, anytime you got a biphase violation, you have lost data or you have an error in data. Eye narrowing near failure, so we've got an indication of that. Of course, I left that validity bit in circuit, so we're still showing that error. So all of this is being presented to you to help you track down where and why these pops and glitches are coming into play. Now, I'm sure there'll be some questions about this, but I'm going to move on here to the next slide in the PowerPoint and talk about bit transparent path. This is quite straightforward. What we're looking at here, again, is D-scope and PC. But now a bit transparent digital system. In other words, a router, a patch bay, a piece of cable. So the stimulus now will be a pseudo-random sequence. In other words, a number, a known number. We're going to put that known number, those zeros and ones, into one side. Then we're going to turn around and we're going to take a look and see whether that same number is coming out the other end of the path. So back to the D-scope for live measurements. Call up my transparent path on my shortcut button. And there we have it. Now, the way this is accomplished is rather than have a generator, sinusoid or square wave or whatever we choose when we're in the generator mode, we use something called channel check. And in this case, it's going to be 24 bits. And we're going to put it down the path. And then on the other side, we're going to take a look at channel check over here. And we've got 2 green lights. So this is all we need to know. We're putting in a number on one end. The green lights mean we've got the same number coming out the other end. Now, what I can do, let me try to degrade this, see if I can accomplish that. Wrong button, Doug. Sorry about that. Actually, it's right up here. So let's add, again, some low-frequency sine noise here. I'm going to add, say, 100 nanoseconds here. And we can start to see that we've got errors. Now, this is interesting because the errors that we're seeing here are actually only occurring on the B channel. I don't know if you caught those or not, but I'm right on the edge here. I'm trying to make a point here in that what we're experiencing here are errors that are just happening on the B channel. So if you were trying to solve this problem with a scope or your distortion analyzer or some other conventional method, there we go. Now we're starting to see those errors only on the B channel. You would not come to the conclusion that there's something wrong with the carrier because you've got errors only on one channel. You would think, oh, I got a piece of equipment that's got a problem on one channel. So this just shows you again the power that you have when you use these types of tools. And I think that is the end of my presentation. Let me take a look and see if that is the case. Yeah, just to recap. So we talked about what causes pops and glitches. We talked a little bit about the history, and we dove into the format, channel status, my favorite thing, the eye pattern, and of course the last thing we talked about was detecting pops and glitches. So now I think what I'll do, if Simon hasn't gone to sleep, I will turn the presentation back over to him, and he's got some other things he'd like to mention to you. Thanks.
I'm still wide awake, Doug. Thank you very much. So yes, we've taken a look at the specific context of attempting to detect and correct pops and glitches in a digital audio stream. There are some further considerations that warrant further discussion in the context of broadcast audio. We won't have time to go into those today, but I just wanted to at least bring them to your attention. Now, the first of those considerations is what we might do in the context of testing a live broadcast stream. Now, we've seen from Doug that many of the analysis functions that DScope and DSA1 afford you can be used in testing a live broadcast stream, particularly from the point of view of analysing the carrier and the metadata. But of course the audio data in a live broadcast stream will be program material and not test tones, which makes analysing the quality of an audio transmission a little difficult. And in fact, what you really need to do is to be able to find a short space of time, maybe a couple of seconds or so, during a quiet period, perhaps in the night, where you can use a very special type of test tone. In our case, we normally recommend a multi-tone, in order to quantify the performance of the entire signal path in a very short space of time. And this is something that we have some further information on our Prism Sound website. This is a rather lengthy URL, for which I do apologise. We will actually be uploading this recording once we have produced it. So if you're frantically scribbling this URL down and don't get time to complete it, then don't worry, because this will be available on the recording once we have uploaded it. Sorry. You may also be interested in analysing the audio performance of individual components and systems within your broadcast audio signal chain, which includes the susceptibility to carrier degradations and also the performance of the AES generator itself. And this is all covered under a range of test methodologies, test recommendations known as the AES3 recommendations. And again, there is some further information on that on our website, and there is a complete suite of semi-automated audio tests within the DScope software that allows you to perform functional tests according to the AES3 specifications or recommendations, more accurately. And finally, it's not always going to be possible to prevent pops and glitches in all situations. You may already have source material that has been recorded and pops and glitches were present on the day. You may not have had sufficient time to use your test and measurement gear to track down the pops and glitches, and there are some tools out there that can help you with that. In particular, I'll mention a company called CEDA, who specialise in correcting audible artifacts such as pops and glitches. And there are two main CEDA tools. The CEDA Cambridge system allows you to correct pops and glitches in real time, and there is also offline processing available. And in fact, there is a division of Prism Sound called SADI that specialises in producing audio recording workstations, and those SADI workstations can be fitted with CEDA processing tools for correcting pops and glitches after the material has been recorded. These areas are worthy of much further discussion, but we won't go into those today. What I'd just like to do now is say thank you very much for your attention during today's session. I hope you found it interesting and enlightening. I'd like to say thank you to Doug in Texas for taking us through today's presentation, and we hope to see you on another Prism Sound webinar in the not too distant future. So once again, thank you all for now, and goodbye.